or
Yeah, I'll give you StreamYard
or
in a
that way?
second. Let me give you
Alright.
StreamYard. StreamYard here. StreamYard here. Click on the HW link. You see the link that ends in HW.
Where
Do you
is
see
that
it?
link?
It's in the side chat,
Where'd you put the link?
the general VC side chat. You can see it in the stream. Oh, you don't see the stream? Let me give you the stream too.
Yeah, I see. I see. Don't worry. I
Okay.
was just in the wrong chat.
Oh, okay.
I was on another Discord channel. Like, where is it? Oh,
Okay. So today's stream was actually they want to take it down because I was watching Kalili. They say it's illegal to show Kalili, like Professor Kalili.
damn. That's some illegality right there.
Yeah.
I'm crying. Okay, yeah. But I understand.
Mm-hmm. All right, you're on stage.
Nice. So, okay. But did you conclude anything from that stream?
Just a little bit. Look, we started watching another video. Yeah, this one. So, the law of falling bodies, the mechanical universe, and this is actually. Can you see it? Yeah, you should be able to see it. This is actually Leonardo da Vinci. This is Leonardo da Vinci. He said in the first period it's 1 unit. Second period it's 2 units. He didn't do an experiment. I mean, he was just like pulling this out of thin air. Let's see.
3 units of distance in the second interval, 5 units of distance in the third interval.
So Da Vinci said it's 1, 2, 3, and Galileo said
falling 1 unit of distance in the first time interval, 3 units of distance in the
it's
second.
1,
5
3,
units of distance in the third.
5.
Interesting. Yeah.
Which this ends up being correct because 1 plus 3 is 4, and that's 2 squared.
Yeah.
And so 5 plus 4 is 9, which is 3 squared.
That's funny because it's also like the Fibonacci sequence.
I know.
Yeah,
Well, I don't. I think this is just. Is this Fibonacci?
It's not exactly, but because then you get to 8. Yeah,
Fibonacci is
you
1
get
plus
to
0 is
8.
1, and then 1
Yeah.
plus
No,
2
it's not.
is
It's
3.
not. It just seemed like it.
Oh, okay.
I was just looking at this as like
Oh,
market.
anyway, he just says it's the odd numbers, doesn't he? 1, 3. Each one is the next odd number, which is 7. Is it? So 7
it's not
plus
really
9 is 16. Yeah, it's incredible. With
it works.
yeah, so it's just the odd numbers. Like the first time I saw this video, I was like,
Oh.
how could these people think in such weird terms and get the wrong answers? But then I was like, this is the right answer. It's the odd numbers. Why didn't they teach me this in kindergarten?
Yeah, it's like it's very easy to learn it like that.
But it's like where is this coming from? Like that's the way gravity works. Gravity works in odd numbers.
Yeah,
Like,
it's very intuitive even.
I don't know. Anyway, let's see what he says.
And so on. In other words, according to Galileo, the distance fallen is proportional to the odd numbers. Galileo reached his conclusions after a brilliant series of experiments in which he timed a ball as it rolled down steeper and steeper inclines, moving closer and closer to the vertical.
He just noticed it through experiments. It's not like he came up with it from a thought experiment.
Path of a free falling body. Galileo's law of odd numbers can be seen in action in a very...
It's the law of odd numbers. Can you believe it? Gravity works by the law of odd numbers.
Yeah,
you never knew this. There's no way you ever knew this.
unlikely
No.
place. It's a place that would have amazed that great Renaissance thinker even more than the surface of the moon. At Magic Mountain Amusement Park in Southern California, customers gladly pay for the privilege of plummeting through space under the influence of gravity.
No, I'll buy you lots of cotton candy. We could feed the ducks. No, I don't think I want to do this. Oh no.
Actually, it's part of life's free. What the customers have really paid for is an arrangement that allows them to survive. At any rate, what about Galileo?
This is 1985 computer animation. This is state of the art.
Yeah, I'm thinking about one thing. Can you like short the market or with the law of odd numbers? Maybe it works.
Yeah, maybe.
If this is 1
Yeah.
unit of distance,
Oh,
it should
check
be
this
3.
out.
This should be 5, and so on,
Wow.
which is exactly what they are. Galileo was right.
It's like the first time I heard this, I was like, what? What am I missing? What is going on?
In successive intervals of time, the distances fallen do follow the odd numbers. But there's something else going on here that Galileo understood perfectly. Notice the total distance fallen at each point.
Now that's the amazing thing.
After the first time interval, 1 unit of distance. After the second interval,
So this is 1
Yeah.
squared, 2 squared, 3 squared. Unbelievable.
4 units of distance. After the third,
So you didn't know that there is a ratio, like you didn't know that the square of the integers, you can also do the addition of the odd numbers and get the same values, like the same like spans. Unbelievable.
interval, 9 units. After the fourth, 16 units. In other words, at the end of each interval, the total distance fallen is 1, 4, 9, 16, 25, and so on. And those numbers, of course, are the perfect squares. So the distance fallen is proportional to the square of time. And in that form, Galileo's law can be written as a simple equation.
And this is good that he didn't use 1 meter. If you just say 1 unit, whatever that distance is, you call that the unit.
Yeah.
So everything is proportional to that unit. Whatever it is, you don't care. And this is the proportionality. So you don't say distance is equal to. You don't care what it's equal to. You just say it's proportional to. And then you whatever the equation is, it's proportional to, and then you work out the rest. Unbelievable.
Using S for distance and T for time. S of T equals.
So the distance as a function of time is equal to, well, it's proportional to t squared, or it's equal to some constant times t squared. Do you understand this equation?
Yeah, perfectly.
Yeah, okay.
Simple.
Equals CT squared.
Right, but they didn't go through the proportionality. The first, like I was watching a YouTube video where he said proportional to something just means equal to a constant times that thing. No one ever taught me that until today. I didn't know this.
Really?
No, you knew that proportional to means equal to a constant times whatever is.
Yeah, I mean, it does not necessarily a constant.
What could it be?
Yeah,
Otherwise,
it
it's not
can be-
proportional to.
Well, it can be a permanently increasing variable.
No, then it's not proportional. Proportional to, the definition of proportional to, that means equal
Okay,
to
yeah,
a
it has to be a
time.
constant. Yeah.
Yeah.
This means we're talking about distance.
I mean, proportional to means linearly proportional to, because proportional to could be
I mean,
anything.
this is squares proportional.
Right. So I think they should say linearly proportional or linearly correlates with, and this is the linear, like agent or multiplier. What do you call it? Linear. What do you call this thing when you multiply? Not an agent. Constant, but it has a name, like a multiplier, not a multiplier. I forgot the name. It has a name.
As a function of time. The distance, S, increases as the square of time, T squared. This constant,
That's the main thing.
C, is numerically equal to the distance a body falls in the first second. That's 16 feet, or just a little.
Oh my God! So this is the unit distance, the 1 unit distance. C is the 1 unit distance.
Under 5 meters.
Wait, what is it?
In the first second. That's 16 feet, or just a little under 5 meters.
It's six. It ends up being so much. In 1 second, it falls 16 feet. Wow.
We know that at any point in the fall, the distance fallen is equal to c times the square of the time. So after 2 seconds, the distance fallen equals c times 2 squared, or 4c.
Wow. After 2 seconds, it's 4 times C. Yeah.
If we use 16 for c, we know that they've fallen 64 feet.
Since we know in the first unit it falls 16 feet, then it must be 64 feet after 2 seconds. Amazing.
Again, this symbol emphasizes that for any time t, we can find the value of s. At this point, even the most petrified free fall rider can depend on us to tell her exactly how far she has fallen at each instant
She has a good body.
during the plunge.
What if you want
Yeah.
nothing?
Like in those days, everybody was thin. It's like, look,
Yeah,
everybody,
but
everyone is
also
thin.
they shows people for the TV that were like purposely.
But still, I think everybody in 1985, I think everyone was thinner than they are today. Like today, I think everyone has gotten much more fat.
But the more discerning
But
rider
she's taking it. Oh, this is the same ride. This is when she was panicking during the first
Yeah.
ride.
may also want to know how fast she's falling. Her speed is the distance she falls divided by the time it takes.
Wait, what? Her speed? That's an average speed. The average speed is the total distance over the total time. That's just the average speed. Why do you care about that?
For example, since she falls 64 feet during the first 2 seconds, her average speed must be 32.
Yeah, her average speed. But why would we care about her average? So the next thing we're going to discover is something strange about her average speed.
feet per second. But that's only her average speed during the first 2 seconds. At the beginning, she was standing still. And at the end of 2 seconds, she was falling much faster than 32 feet per second. Obviously, what this woman really wants to know is not her average speed, but her exact or instant.
Exactly. She doesn't care about her average speed. She wants to know about her exact, which is the derivative, the instantaneous
speed at any given time. However, if we try to use the same equation dividing the change in distance by the change in time, we have a serious problem. At any instant during the fall, let's say
I mean, I don't know if we have a serious problem. We're just getting the average and not the instantaneous.
Exactly 1.5 seconds. Change in distance and time is 0.
This is an amazing way of teaching. Like I never learned
that's why we should replace school with YouTube.
Yeah.
Just like YouTube, and you find a way to make sure that the students are actually watching.
Yeah.
Like a camera.
No, just give
their
them
eyes.
No, just test them. Anyway, so what is he saying? Let me hear this again.
Any instant during the fall, let's say at exactly 1.5 seconds. Change.
Oh, good. So he's going to calculate the instantaneous speed at exactly 1.5 seconds.
Change in distance and time is 0. So a formula that determines
change in distance and time is 0. Oh, it's 0 over 0. Oh, he's saying that's the problem, that it's 0 over 0.
Speed by dividing the change in distance between point A and point B by the change in time is of little use when we have a point A, but no separate point B to work with.
I'm not following. Are you following what he's trying to get?
At any instant during the fall, let's say at exactly 1.5 seconds, change in distance and time is 0. So a formula that determines speed.
The change in distance and time is 0. Well, this is the definition of instantaneous. So a formula that determines speed.
By dividing the change in distance between point A and point B by the change in time is of little use when we have a point A, but no separate point B to work with. To make matters worse, both the top and the bottom of the fraction.
He's saying A and B are the same point because they're instantaneously close to each other, so it's the distance is 0.
Would be 0. And of course, dividing by 0 is a mathematical disaster.
Okay, so that's what he's referring to. So it's 0 divided by 0. Okay, yeah.
Well, that's just
at first glance, perhaps the expression instantaneous speed is a contradiction in terms. And yet, common sense tells us that as long as an object is moving, it must have a certain speed at every instant. The problem is much more than a clever play on words. It's a dilemma that plagued mathematicians for thousands of years.
Unbelievable.
But there is
he's teaching differential calculus from first principles. Unbelievable.
Way to solve it. Instead of asking the instantaneous speed at an exact time t, we'll ask, What is the woman's average speed between time t and a point h seconds later at time t plus h?
Oh my God, is he gonna do? he's doing,
Yeah, it's
he's
taking derivatives.
he's doing derivatives. He's gonna do the limit and
Yeah, but
stuff.
it's basically doing like the thought process of Newton, which is good.
Yeah, yeah.
Now, the change in time is simply h seconds. If the distance fallen at any time t equals c times t squared, then the distance fallen at time t plus h must equal c times t plus h squared.
Let's see. Okay. Yeah, this is literally a derivative. So okay, so we have s at t, and we have s at t plus h. S at t plus h is c times t plus h squared. S at t should just be c times t squared. Why isn't he showing what s at t is? Anyway, so s at t and then s at t plus h. What is going on here?
Minus S and T.
It's equal to negative.
No, I don't think the equals should be there.
Oh, what is that? Oh,
I need to
it's just minus.
Oh,
Okay.
God, the equals.
So
It
it's
should not be there.
there's another equal. Anyway, so he's doing
That goes
oh, he's
for
doing delta. I get it. Okay. So this is delta x and h is delta t. So h is delta t. So this is delta t and this is delta x or delta y, whatever. So it's c times t plus h squared minus ct squared. Very good. And that's the average instantaneous speed. That's good. So t plus h squared is t plus h times t plus h, which is t squared plus 2th plus h squared. Right. Multiply by c. Okay. Good. So ct squared plus 2cth plus ch squared minus
Yeah,
ct
you're gonna
squared. So
get
the ct squares drop
CT.
out. Okay. Good. What's going to happen? Oh, h. There's a bunch of h's that go away.
Yeah.
Good. All right. So average speed is 2ct plus ch. Okay, and
Yeah, but you
h
can
will
cut
go to
CH.
0, right? H will go to 0. So it's just going to be 2ct. Unbelievable.
Problem
Yeah.
is solved. We can calculate her average speed starting at any time t over any interval h. H can be 1 second, half a second, a tenth of a second, or even 0. Because now we're not dividing by 0.
Wow. Yeah, but before you were dividing by 0.
Yeah.
Because when you dropped out all the h's, that was division by 0. But it's okay to divide by 0, I think, when it's literally 0 divided by 0. It's like h divided by
Yeah,
h.
when it's the same
Yeah,
0
it's
divided by
literally the same
something.
value. It's fine, apparently. Yeah.
And now we can let the h interval shrink smaller and smaller and smaller, even to the ultimate limit. And at that instant, we've calculated a derivative as the interval completely shrinks to 0.
I mean, anything is a derivative. It just means derived from. What you calculated is the instantaneous, I would say, velocity, or in general, the instantaneous change. The function that describes the instantaneous change of the original function.
H is exactly 0. We have found that at any time t, her instantaneous speed, which we'll call v, is 2ct.
Unbelievable.
Using the value of 16 for c, we can now tell her, Madam, don't worry.
Okay, so we know we measured that the first second the unit distance is 16. So it's 2ct. So after 1 second, t is 1. 2 times c is 16 times 2. So it's like 32 or something. So it's 32 feet per second at the end of the first second.
Worry about a thing.
He called her madam. Like he wouldn't do that today because I don't know if that's how she identifies. He might get canceled.
The distance you've fallen is 16 times t squared feet, and your speed at each instant is simply 32.
So the distance is c times t squared. We know c is just the unit, which we discovered is 16 after 1 second. So let's say after 1 second, it's 16 feet, but the velocity is 32 feet.
Times t feet per second. Obviously, she's impressed. How did you figure all that out?
She's impressed. How did you figure all this out? What do you mean? We just went through it step by step. Weren't you listening?
She might ask. It was nothing really. All we had to do was to invent the derivative. In common usage, the word derivative means arises from, as in the phrase, fudge is a derivative of chocolate.
Oh my God. He's actually following the logic of what I said.
Is the derivative.
But in mathematics, the word
Fudge is the derivative of chocolate.
has an exact technical meaning, which amounts to this.
Okay, it has technical meaning. All right.
It's the rate at which something is changing.
Right. It's the rate at which something is
The
changing.
speed of the falling lady was the derivative of her distance.
Falling lady. Oh my God. The speed of the falling lady was the derivative of her distance
From the top.
from
In other
the
words,
top.
speed is the derivative of distance.
Wow. Speed is the derivative of distance. Holy moly. This is like the most first principles discussion I've heard in my entire life of anything. Amazing. This series, you know, that it's a very long series. They go into quantum mechanics. They do everything. Really impressive. Really, really amazing production quality. Let me just plug in my power.
At first, when we discussed her average speed, we were merely doing algebra, simply plugging numbers into the speed equals distance divided by time equation. But when we began to work with an interval of duration, h, and at the right moment let h shrink to 0, we were calculating a derivative, and we entered the world of differential calculus. Differential calculus is the mathematics of using derivatives.
Amazing. He calls it differential calculus. I thought calculus by itself just means differential. But apparently not.
No, there is integrals and yeah.
Oh, there's differential and there
I
is
mean, but
no.
that's technically part of differential calculus.
Right.
Yeah, I don't know.
Okay. Yeah.
The process of calculating a derivative is called differentiation. Of course, the concept of a derivative doesn't apply only to a body in motion. Conceivably, a derivative could be calculated that represents the rate of change in the population density of dolphins versus the temperature of the ocean, or the
Wow.
rate of change in the volume of a balloon versus its surface area, or the rate of change in the cost of a pizza.
Is that the same lady?
A balloon versus its surface area.
It's the same
Is it?
guy.
Is
It's
it the same
that
guy
was
from
helping her.
the Luna Park?
Temperature of the ocean.
From
Yeah.
the falling
Or the rate of
machine?
change in the
Yeah,
volume of
that's
a
the
balloon.
Are
same
these the
guy.
same kids?
Yeah, I think
So everybody's an
they're the
actor.
same kids.
So it's all an
Yeah.
act.
Yeah.
We cannot
All
trust
an
anything
act.
they do or say.
Oh, crisis
Surface
actress.
Or the rate
Yeah,
of
but
change
she
in the
has
volume.
like something in her teeth.
In her teeth?
Yeah,
versus
she's
its surface
like
area.
she has like the
Bugs
some
Bunny
teeth.
teeth, you mean?
Yeah, she has funny teeth to appear like a different person.
Oh, you think so?
Or the rate of
Yeah.
change in the cost of a pizza versus its diameter.
The rate of change in the cost of the pizza versus its diameter. Jesus.
In other words, a derivative can be calculated for almost any situation in which one quantity changes as another quantity increases or decreases. To get from distance to speed, we calculated a derivative. But what about the acceleration of a falling body? To get from speed to acceleration, we do the same thing all over again. If v has
But this is just acceleration, but this is gravitational acceleration. And still we need to go to forced acceleration to talk about F
Yeah,
equals
but
mc.
gravitational acceleration and force, it's
Right. So you
gravitation is acceleration, so it's constant.
well, we'll see how.
Yeah,
I mean, yeah. I mean,
I always had a problem of framing it like mathematically it's the same thing, but physically it's not the same thing.
you mean gravitational acceleration versus
Versus,
force acceleration?
yeah, mathematically you can make them the same, but physically they're different. obviously.
I don't know. I think Newton got F equals ma from gravity. Where? How else could he get it?
Uh, I mean, he generalized it as a general principle. Like mathematically, it's correct to do that. It's just the physical part, because you
Anyway,
have to always say
so
that mathematics is the
but
more
but but,
general.
but wait. So we need. I really need to see the derivation. This is why I really need to look at
Okay, yeah,
Principia.
it's rather simple. Yeah.
No, but the question is, in Principia, did he derive F equals ma from from
Oh,
Galileo's
that's true.
gravity?
He might have.
I don't. How else? Because
So
Newton was
probably it wasn't the apple, as they say.
no, but Newton was not an experimentalist. He didn't conduct
No, he conducted experiments. He conducted experiments about light, I think.
but not
But,
about
yeah.
falling bodies. He didn't have experiments with falling bodies.
Yeah, that's probably because someone else had already done that for him.
Right. So he took Galileo and he
Yeah,
derived F equals ma. I think we'll see. Let's see.
yeah, probably.
They're probably going to discuss it. Let's see.
as a function of t equals 2ct. Then v of t plus h equals 2c times t.
Okay, we're doing acceleration now. So now he's saying, okay, what is the acceleration? Let's talk about the instantaneous acceleration. So he's saying, well, what is he saying? So velocity as a function of time is 2ct. That is the velocity that we discovered just from discussing distance. And distance we got from experiments. So this is experimental. This is experimental. This is empirical. This is not a thought. There's no thoughts behind this. That you could not have derived any of this from first principles. You needed Galileo to do an experiment with the plank, with the tilted plank, and with the water. Did you see how he did it with the water?
Yeah, oh, the water. I didn't see the
He
water.
used water. He used to fill up water in a cup, and then he weighted the amount of water in order to measure time. That was his measurement of time.
Oh,
So
that's cool.
that was his clock, yeah. He invented a water clock, very similar to the rubber ducky. Anyway, so velocity as a function of time, empirically we know we derived it as a derivative, it's 2ct. So what is the acceleration?
Equals 2ct. Then v of t plus h equals.
So now, okay, that's average. Now let's talk about the velocity at t plus h. It's 2c times t plus h for any h, and we can reduce h to 0 and see the instantaneous acceleration.
2c times t plus h.
So what did they do? Okay, so they're multiplying by 2c. So 2ct plus 2ch. So they're replacing the equation. So it was so v plus 2h minus v of t divided by h. That's the average acceleration over h. Amazing. So v of 2 plus h is 2ct plus 2ch minus I need to keep going back and forth. Minus v of t is 2ct. Okay.
Yeah.
So 2ct, 2ct drop out. So it's 2ch over h. It's just 2c. Amazing. So and it just ends up being 2c, a constant.
A of t.
A instantaneous for any t is a constant. So Galileo couldn't have done this. Galileo could
Yeah.
not have known this. So this is Newton, probably.
Yeah.
I don't know.
E equals 2c. But look at what's happened. First, we found that the distance s keeps increasing. It depends on time. If t changes, s changes. The speed, v, also keeps increasing with time. But now we found that the acceleration, a, doesn't depend on time at all. It's simply a constant.
Amazing. Wait, so either Newton used, what did he use? He didn't have any data. Did he have access to Galileo's data? Or did Galileo figure this out? But Galileo didn't have derivatives.
No, Galileo couldn't have figured this out.
No. So, but
No.
whose data did Newton use? Unless,
Yeah,
unless,
probably
no.
Galileo's.
So Galileo had the odd numbers rule. So Newton started from the odd numbers. That's all he needed. Okay. He got it from that.
Yeah.
A equals 2c, regardless of the value of t.
Plus the first unit. Well, that is the first unit. So one is okay.
A is always the same. We've finally done it. We figured out that the result of gravity is constant acceleration. We set out to answer 3 questions about a falling body. How far, how fast, and how fast is it getting faster? How far we found out pretty easily, just by watching our falling lady. We even
Lady, the poor lady.
found her average speed just by using algebra. But to find out precisely how
Just by using algebra. What does it mean by algebra? Like the series, the odd numbers, I guess?
fast a body goes at
Yeah.
each instant. And
Average speed, 64 feet divided by 2 seconds. That's average. Yeah, we did the average speed in the beginning. He's reviewing.
to find out how fast it gets faster,
He's reviewing without saying let's review. That's not a good. You should always say let's review.
we needed our marvelous new mathematical tool, the derivative. Using the derivative, we have discovered the most elegant way to describe falling motion. Bodies fall with constant acceleration. Because that acceleration is so important, it has its own symbol, a small g. And g is equal to 2c. Now we can put all 3 statements of the law of falling bodies
And C is 16 feet.
in their final form
So so G is 32 feet. Okay.
by replacing c with 1/2 g.
Wait, why are you replacing C with 1/2 G? So C, why don't you call, wait, so, oh, G is the acceleration is called G. Oh, G is the acceleration. So because you want G to be the acceleration, which is 32 feet per second,
Now we can put all 3 statements of the law of falling bodies in their final form.
and C is half of that because 2C is G. So 2C is G. So C is half G. Okay,
Replacing c
sorry. So G is half C because 2C is G. Okay.
with 1/2 g.
There's no way we went through this in high school, which is
No.
so how did they teach us this in high school? Because they did teach us this in high school. They did derive it from first principles. They wouldn't have just given us the equation, or did they? They just gave us the equation?
I don't know. It's a good question. If they taught us this, I don't remember, and I don't know anyone that remembers.
Right. No, they could not have taught us this because
What did they do? It's
we
not
didn't do
impossible.
no, we
Like,
didn't do we didn't do derivatives in high school physics. So because you don't have derivatives in high
physics,
school
no.
physics, no, but what they did do is using a graph. So you can graph and see, you can see that the velocity is linear, and then you can do you can just do the angle. You can look at the slope of this line and you can see and get the
Mhm.
acceleration. And
Yeah.
this is just the area under, this is what do you call this? A squared. When you graph a square, what do you call it? Not a
That's the area under the
parabola.
curve.
This is a parabola, and they did teach us about the parabola that it has something about a parabola. They did teach us to. This is just the area. I don't remember. Okay, whatever.
Yeah, you're
He
thinking about like the integral,
No, no,
the
no,
area from one place to the
no. But
other.
this is the integral of. I mean, whichever direction you take, like upwards is the integral, downwards is the derivative.
Hmm.
So if you start with the constant acceleration, it's easy to do the area under the curve and get a linear, and then you do the area under the curve and you get a parabola.
Yeah,
The question is, how do you get a parabola from doing the area under the curve? I don't think we.
I mean, don't get the parabola. You get like you get a value that is t squared.
How do you get t squared? Like I don't.
It's
I
just two t
remember.
on the. It's like
Remember.
it's a triangle. It's just a triangle.
No, this is a triangle. This is a
Yeah,
triangle. How do you get from
yeah, but the area of the triangle. You to st is the area of the triangle.
st?
Yeah,
St. This is a parabola. Oh, it's the area of the triangle. But how do you know that the area of the triangle is a parabola?
I mean, the area of triangle is not a parabola, but in terms of mathematical,
No, the area under a triangle is I mean, the area under a slope, under a constant slope, is a parabola.
I mean, it's the parabola. It's the value of the parabola at the point.
No, no, no. The area under the curve.
Okay,
The
the area under the
area.
curve at a certain point is the value of the parabola at that point.
Yes. Anyway, anyway, I'll continue.
According to the law of falling bodies, a body falls with constant acceleration, with speed proportional to time, and falls a distance proportional.
Speed linearly proportional to time. But Galileo could not have known this, but Newton could have figured it out just from the data, the simple law of odd numbers.
To the square of time. That kind of motion is called uniformly accelerated motion.
Oh, very nice. This is uniform acceleration. Wow.
It is difficult, but not quite impossible, to discover all of these facts about uniformly accelerated motion without using differential calculus.
Oh, so he did get it. So Galileo, this is Galileo. There's no Newtonian mechanics here. So this is just Galileo. So Galileo did know
Oh,
this.
Galileo already knew this. No.
I think he did without he says without using differential calculus. Let's
Oh,
see.
but he didn't
And yet-
have the calculus.
Fine. Look. He says you can know
So
this
you
with.
only used like the law of odd numbers to get this. That is
No, no, no. He says, look, it's difficult, but not quite impossible
yeah.
To discover all of these
to
facts
discover
about
all these facts about uniformly accelerated
motion without using
motion
differential
without
calculus.
using differential.
And yet,
Let's see.
Galileo understood all of these facts.
How? How did Galileo knew all these facts? He didn't have differential calculus. How did he figure it out?
In fact, nearly 300 years before Galileo, a French
he
scholar
could
named Nicole had worked out the behavior of uniformly accelerated motion.
Oh my God, I don't believe it. A French scholar 300 years before Galileo?
You can see it's French for the quality of the painting.
Who? What was his name?
For Galileo,
Looks like a
French scholar
woman.
named
Yeah,
Nicole
looks like it has
had worked out the
breasts.
behavior of uniformly.
Named Nicole?
Yeah, it's a woman.
Nicole Orr. His name is Nicole Orr.
Nearly 300 years before Galileo, a French scholar named Nicole had worked out the behavior.
Orain. Orain.
Not a me. It's a she.
No.
It's a she. Yes, that's a woman.
Nicole Orain? Orain means of rain. Rain is a place.
Oresme.
Wait, you should know Orain. You know rain?
Orain. No.
Rain. Rain.
Rain.
No,
Rain, yeah.
not Spanish. Rain is French.
Rain.
Uniform
Anyway, worked out the behavior of uniformly
accelerated motion.
accelerated.
Orain and Galileo used nearly identical mathematical methods to analyze the problem. Their methods were based not on algebraic equations, but on proportions.
So Galileo just copied her.
Pretty much. But wait a minute.
Oh,
Is this how they got it? Like using some sort of magic geometry?
yeah, basically.
Wow.
proportions between quantities and on
I mean,
geometric
it's just geometry in the end of the day. It's just that you
The
find a
derivative was
clever
invented a
way
generation
to
after
explain it with to translate it into maths.
Wait, what is he saying now?
quantities and on geometric figures.
So if we read Principia, we'll probably see this derivation because Principia is written without differential calculus. It's only using geometric, just geometry.
The derivative was invented a generation after Galileo's death by Sir Isaac Newton.
A decade after? Just a decade after his death?
Wait, the
The derivative
derivative
was
was
invented
invented the decade after Newton's
A
death.
generation after. Okay, that's like a generation is what? A
Wait,
decade or
wait.
two decades.
generation after Galileo's death by Sir
Oh,
Isaac Newton
August.
and Gottfried Wilhelm von Leibniz. With this powerful new
Von
method of
Leibniz. Leads with powerful.
Yeah, they invented it at the same time, supposedly.
Yeah.
even more complicated kinds of motion could easily be analyzed.
It
Describing
was the
uniformly accelerated
aliens.
motion became positively
I want to see the geometric derivation of the derivative.
simple.
Without derivatives, it's difficult to understand what acceleration means, much less describe uniformly accelerated motion and work out all of its consequences. And yet,
Look, he wrote everything on the board. He derived it for the class, but this is college level.
it's exactly what O'Reilly and Galileo did. They described uniformly accelerated motion and worked out all of its consequences. It was an act of sheer genius. One of the jobs
Are you gonna teach it, or are you gonna just tell us it's genius? Like, I'd like to know how they did it.
Oh, I had like teachers like that.
We can ask ChatGPT how do you derive acceleration? How did Galileo? Let's ask ChatGPT how did Galileo? Let's see if ChatGPT
Oh,
knows
it's
it.
not difficult. Like the acceleration, we already know. It's the law of the odd numbers.
Let's see
Galileo-
how did Galileo derive acceleration of a falling body? Let's see if ChatGPT knows. Okay, so Galileo Galilei's derivation of acceleration of a falling body was groundbreaking contribution to physics, laying the foundation for classical mechanics. His approach combined experimental observation with mathematical reasoning, leading to his discovery for the laws of motion. So the problem with Aristotelian physics, okay, we know what the Aristotelian. Galileo's inclined plane, that's fine. Experiment, he rolled, that's fine. Observation, that's fine. Mathematical derivation. So he noticed that it's proportional to t squared or equal to 1/2 at squared. No, he did not. In modern terms, yeah, thank you. But what did Galileo know? Acceleration is so ChatGPT doesn't know. Pendulum experiments. Nothing to do with it. Conclusion: ChatGPT does not know how he did it. References: the mathematical principles of natural philosophy. Galileo, very short introduction. Okay, so ChatGPT doesn't know, so we need to maybe say geometrically.
Okay, give me 5 minutes. You can continue,
Okay,
but I have to do it.
okay. So how did Galileo derive acceleration of a falling body? Geometrically. Galileo's geometric approach, initial understanding and hypothesis. Galileo hypothesized that a falling body accelerates uniformly. Really, meaning that the speed of the object increases by the same amount in each equal time interval. He aimed to demonstrate this using geometric reasoning, which was the preferred method of mathematical proof in his time. Concept of uniform acceleration. Galileo envisioned, wait a minute, so if it's 1, 3, 5, so 1 plus 2 is 3, 3 plus, it's always 2. That's the 2. So it's always 2. It's always increasing by the same amount. So it's 1, 3, 5. It's always increasing. That's why it's odd. It's always increasing by 2. Oh my God, that's the reason. It's increasing by the same amount. So that's an indication. It's increasing by the same amount. And the increment is the change. Galileo envisioned a body falling from rest and increasing its velocity uniformly over time. He reasoned that if an object falls with uniform acceleration, the distance it travels in any given time interval is proportional to the square of the time elapsed. Why? Why? Why would you say that? I mean, he discovered that, but why would you say that? Okay, so it's a thought experiment. You're saying it feels like it should be constant acceleration. So let's assume it's constant acceleration. If it's constant acceleration, then it should be the square of the time.
Back.
Why? Look, I found okay. I asked ChatGPT geometrically. So ChatGPT says concept. So he says Galileo envisioned a falling body at rest, increasing velocity uniformly. He assumed He assumed uniform acceleration. He reasoned that if an object falls with uniform acceleration, the distance it travels in any given time interval is proportional to the square of the time elapsed. Why is that? That doesn't make any sense.
Yeah, distance is squared.
Why? But why? Why would
Distance
you?
to acceleration.
Why would you say that? Under constant acceleration,
Yeah.
the distance is related to the square of the time. How would you figure this out? Let's see, geometric representation. Galileo represented the motion of a falling body using a line segment, where the length of the segment represented time, and the area under the curve, a triangle in this case, represented the distance traveled. Okay, so it's a slope. So y
Yeah,
equals
the neighbor's cat is attacking my cat.
what? What did you say? Are you there? What did you say? The neighbor is you're under attack? Where are you? What happened? Oh, the neighbor's cat is attacking your cat. I thought the neighbor's tank is attacking your country. It's like the neighbor's tank is attacking your country? Are you on the border of two countries? You're not on the border of any war. I hope not. No, the neighbor's cat is attacking your cat. Okay. Let's see. We have comments in the comment section. Nicholas says, I'm going to listen to you guys. You guys are smart than me. We're not. Stop it. Distance in one space can be derivative of speed. I don't know. Nicholas, you kill me with your You you destroy my brain. My brain malfunctions. Now, me too. I want to see the geometric derivative. Me too, yeah. Okay, so basically it's a slope. So under constant acceleration, so the speed grows linearly. So the speed, so if you assume constant acceleration, that just means your speed
I'm
grows.
back.
Okay, so is the cat fine?
Yeah, it's fine. It was just like getting ready to attack.
So I thought you were saying my neighbor's tank is attacking my country.
What?
And then you disappeared. I went to Discord and you disappeared, and I said, "What? There's another war breaking between your neighbor's tank and your country?" And then I remembered, wait, you should be. And then I saw you muted, and I said, wait, if you're muted, it can't be that bad. Okay, it's your neighbor's cat is attacking your cat.
Yeah.
That made a little bit more sense. Okay. I was worried. I was like, we have war.
Like another
You're
one. That's
I'm
like,
gonna lose you to a war? No. Anyway, so look at this. So Galileo just assumed. It's really very simple. He assumed constant acceleration, which makes sense. It's a reasonable assumption that the force of gravity it's constant because you always feel the same force. You weigh the same. I would say everything weighs the same at any height. So the force is constant. So that's the proof that the force of acceleration is a constant. The question is it a constant as you accelerate? As your speed changes, are you experiencing the same force of acceleration? That much I don't know, but he assumed yes. It's a leap of faith. So Galileo assumed a constant acceleration. So constant acceleration just means your velocity changes linearly with respect to time. So if it's 1 meters per second at the end of the first unit of distance, no. So not the unit of distance, unit of time. So after 1 unit of time, your velocity is 1 unit of speed, of velocity. After 2 units of time, your velocity is 2 units of velocity. So your velocity is linearly proportional to time. Perfect. So, and that's just a straight line. So Galileo represented the motion of a falling body using a line segment, where the length of the segment represented time, but not the angle. And the area under the curve, a triangle in this case, okay, so he used a triangle instead of, because he probably didn't have Cartesian coordinates. They probably didn't know how to draw X and Y. So all he had was just a triangle. So he said, okay, a triangle represents, a right angle triangle represents the velocity. The velocity increases linearly. Represented, oh no, it's the distance traveled. The area under the curve, how does he know that the area under the curve represents the distance traveled? 1 second. Galileo represented the motion of a falling body using a line segment, where the length of the segment represents time, which is the x coordinate, and the area under the curve, so there's a curve, a triangle that represents the distance. How do you know that? And how do you know that why would you say the area under the curve represents the distance? Why would you say that, Galileo?
Galileo figured that out.
How? How do you know
Geometry.
that the area under the triangle represents the distance traveled? Why would you say that?
Geometry.
I would say because
Triangles.
it's like 1 second, and this is the velocity. So the area is and you already see it's 1/2 AT squared. Everything is in a everything is in a triangle, because 1/2 the area under a triangle is 1/2 base times height. And if it's a right angle, so how is it 1/2 base times height? It's just 1/2 base times height. There's nothing squared. 1/2 base times height. Base is time. What is height? So he doesn't know what the height of the triangle is. Anyway, he considered a linearly increasing velocity where the velocity at any time is proportional to the time itself. If time t is represented by the horizontal axis and velocity v by the vertical axis, the graph of velocity over time is a straight line from the origin as the object starts from rest. So he's now imagining, right, the height of each triangle is the velocity. we need to use the whiteboard. So he's imagining that the height, the velocity is the height of the triangle.
Yeah.
The area under this line gives the total distance traveled. Why is that? Why would you say that? For a
Uh,
uniformly accelerating object, this area is a triangle with the base equal to the total time and the height equal to the final velocity. But you already said that the height is a function of time. So it's t times the constant. And that's why it's 1/2 ct squared. So he can calculate, based on the assumption of constant acceleration, he can calculate the equation 1/2 ct squared. So he has 1/2 ct squared, and he already knows the first unit because he measured it. It's 32 feet. So 32 is 2c, which means it's 1/2 gt squared. So he derived 1/2 gt squared.
think about it. Like, imagine you have an average velocity of 2 meters per second, and you walk 2 meters.
No, but that's not what he did.
No, but I'm trying to
Yeah,
explain
let's
to you why it
I
would be
understand. Yeah, yeah,
the area.
I was thinking. Let's try and draw this. I'm I'm gonna go to this. You can watch on StreamYard if you want. You can see everything on
Yeah, I
StreamYard.
can see it. I can see Lily as destroyed.
Okay, so uh this is Galileo gravitational acceleration. So Galileo said this is time. Okay. And at any point t, this is the height. Let's call it h. But h is the velocity. So let's just call it velocity. So this is velocity. The height is the velocity at any time. And constant acceleration means that the velocity, the height, is v is equal to c times t. This is what constant acceleration looks like. Now, the next question is, he says the area under the curve. One second, who is this? Amnesia. There must be something outside of us that can sustain objects when we are not perceiving them and account for the regularity of our perception. What is that?
It's the universe.
I mean, I call it the permanence assumption. I call it the permanence assumption, or the peekaboo assumption. Babies are amazed when they first figure it out. You were too. That's my assumption. All right. So, all right. So he says the area under this curve is the total distance. So area is equal to distance. Why is that? Well, I mean, you could imagine like the numerical integration, that this is the distance I'm traveling, delta t times right at this instantaneous velocity times delta t. This is the distance that I'm covering. It's v times delta t is delta d. The instantaneous velocity times the delta t is equal to delta d.
Wait.
Okay, you
V
don't need
times
to.
delta t. No, but you're doing delta v times delta t. No.
No, you can just so because of
But
this
you're doing v, but you're doing vt in
v
that
times delta
sharp.
t.
But
This
then
is
what are you
delta t,
calculating?
the area under the
No,
red.
but that's not v. Like that
Yeah,
should.
this is
Wait.
v. The height is v.
Oh
Here,
yeah, right.
we did this. You missed it. One
Yeah,
second.
yeah.
What is he saying? Uh, what's that? I just explained that to you. Okay, VC now.
He doesn't know what peekaboo is, probably.
Yeah, I don't know what's going on with him. Okay, so so um okay, so it makes sense. So delta D is delta A, which right? I mean, you don't need to do any integral calculus. You can just do area under the curve. It's just t. So the area d is equal to the time t times the height v, but v is already you already decided it's ct, which means the area is ct squared. And you already know that after 1 unit, hello, what's up?
What's up? He's not listening.
Amnesia, can you hear me? Amnesia, can you hear me?
Mm-hmm.
What's the question?
What is the Hermes assumption?
That I invented it. Like why how do you know the universe is there when you're not looking? So you don't know. It's just an assumption. It's the permanence assumption that objects are permanent, that they're still there when you're not looking. Oh my god. Why does everyone do that as soon as they walk into a physics discussion? So, do you have any questions, Amnesiac?
I just did one.
What? Do you have any questions?
I just asked one.
I answered. I answered with, like, I don't know what else to say. What do you want me to say? Okay, you don't want to talk? That's fine. All right, let's continue. So it's equal to CT squared, and C, so he discovered that after 1 second, it's 32. Oh my god. Everyone walking into one of our streams always has to scribble on the board. Anyway, so C, how does it go? C is 30. What did he assume? Anyway, whatever. It's what did he assume? So V is equal to CT. Does he know anything about V? Did he measure V? I don't think he measured V, but he knows D. He knows after 1 second he knows it's 32. So he knows 32 is equal to C. So C is 32. What are you doing? Anyway, if C is 32,
I'm here. If that's your.
no, if C is 32, what do we know? We know this is the area, the distance. So distance is 32. He knows it's 32 feet after 1 second. So C must be 32. No, if C is 32, okay, C is 32. So V is 32. Wait, V is 32?
Wait, what are you doing?
I'm trying to get to 1/2 gt. I want to get to 1/2 gt squared. So c is 32 because you know that after 1 second he is at 32 feet. Like, right after 1 second he covered 32 feet. Right, that's
Okay.
right. I'm assuming that. Okay. So distance is ct squared.
Yeah.
No, it's 1/2.
Yeah, it's 1/2.
It's the area. Oh my god, it's divided by 2. That's why I wasn't getting it. Okay, 1/2 ct squared. So 1/2 c. So it's 64. 1/2 c is 32. So 64 is c. So c is 64. If c is 64, so
You know, you
v.
can see 64.
So v 64. If v is 64, then what is a? A is the acceleration per unit. How much do you add? This is the acceleration. How much do you add per 1 unit? What is the slope? Oh, what is the slope? So what is the slope?
The
V
acceleration, you already know the acceleration.
acceleration is c.
Yes.
Slope is c. So c is, well, v is 64. C is 64. So c is 64. Is c 64? Yeah, c is 64.
I found an amazing discovery.
Where's g in this? What am I missing?
Did you know that
GC.
kinetic energy equals the mass of a body times the speed of light squared?
What do you mean? Do I know? I mean, I
No,
don't
that's
know.
wrong.
That's the rest mass. The rest energy. You mean the rest energy? That's not a relativist. Relativistic energy could go to infinity. Did you know that?
Relativistic energy can go to
I mean,
infinity.
is knowledge possible on your view?
Is knowledge possible? What do you mean is knowledge possible? Well, you need to be able to derive E equals mc squared from first principles. Otherwise, you're appealing to authority, which is a logical fallacy. See, we don't even accept F equals ma on this channel. F equals ma is appeal to authority here. Anyway, so how do you get? So what is acceleration? So acceleration is just c. Yeah, acceleration is c, which is 64 meters per second squared. No, it should be. Isn't it 32 feet per second squared? Feet per second squared? Second per second. Why is my c? Okay, let's do this again. So the area under the curve is the distance. Okay, which is 1/2 times velocity. Velocity is ct. So it's 1/2 ct squared. Now we know after 1 second, it's 32. So c is equal to 64. Okay, so c is 64. If c is 64, then v is 64t, which means v is 64 after 1 second. Okay. And a is c, so acceleration is 64 feet per second square. What's going on here? Why is my acceleration? What's going on? What am I missing? C Stannis, are you gonna tell me?
Wait. Okay, so what do you want? What do you want to do? You want to calculate? You want to get the distance, right?
Distance here. Distance is the area under the curve, right?
Okay. Like, come on, man. Like this. Like I'm looking at this and I can hardly make what the hell is going on here anymore.
This is an average day on this channel. Somebody comes in and draws.
Look, okay, here's the deal. You get
Look,
the velocity, right?
otherwise, whatever we're doing is not going to be challenging enough, obviously.
Yeah. You get the velocity. So the velocity. Imagine. So okay, first of all, let's simplify it. Let's imagine constant velocity over time.
No,
Right.
we're just assuming constant acceleration.
No. Let's assume first constant velocity.
What do you mean?
Now let's assume first constant velocity just for the sake of explaining things.
Okay.
So constant velocity. Let's say constant velocity of 2 meters per second.
Let's
And
go to
you
the page.
and you.
Wait, come with me to a new page. Hold on.
Okay.
So this is
You didn't
If
like
it's
the
going to
response?
continue, then that doesn't solve anything.
okay. So under constant velocity, you would draw a rectangle where this is t and this is v. But then
Yeah.
whatever v is, the distance.
So what would be the distance?
It's
It'd
the
be
area,
2
which
times
is just
v, right?
dv. But there's nothing smart you're saying about v. It's just a constant.
Yeah.
But if you assume
It's t
constant
times the
acceleration,
constant. Okay, so now let's do it for well. Imagine that instead of v, you have constant velocity. You have constant acceleration, right?
exactly. So
And
acceleration is equal to constant.
you'd get the velocity on a certain period of time
No,
would
so
be t times acceleration,
here,
right?
this is time. This is instantaneous velocity, but this angle is c. So this velocity
Not
must
one.
be. It's a function of time because it's linearly proportional to time. So v is equal to ct,
Okay, so that's the thing.
right?
Like,
Because
how does it work
this is the
when
acceleration.
you do t over v, but you have constant acceleration? What happens is that you get like if you imagine it, you get like very small rectangles,
What?
and they're just getting bigger and bigger and bigger, which makes a triangle,
Right.
right? Can you draw that?
Yeah, there's the triangle. What?
Yeah, but you're getting like very small rectangles that end up forming a triangle. Can you imagine it,
Right.
right?
So very small rectangles.
No, not
That
like
form.
that.
What do you mean?
Okay, I'll go into the thing and draw it. Wait a minute.
It's gonna be very difficult.
No, it's fine. Okay. So this is loading. Oh, what's going on?
I don't know. You're still there. He left.
Yeah, but this isn't like loading. Let me leave.
Oh, okay.
Okay, whiteboard work. Okay, whiteboard is working. Alright, so why not? Okay, I'm right. So you'd first get a rectangle like this, right? And then you'd go to the next velocity, you'd get a rectangle like this. Wait, no,
Why? But t, the base is t. The height is
yeah,
v. So why would you get
exactly.
rectangles?
Imagine that. I'm telling you. Imagine that the velocity was always this way from here to here. It would be rectangles, but it's not. It's only from here to here. That's why it's a triangle.
Okay. Why do you need? Okay. I I don't need to think about that option. I just imagine the red triangles, and I'm just doing the
Yeah, I mean it's not
well.
the same.
The integral of the red triangles is just the area on of the triangle. So distance is equal to the area, which is just t times the final velocity, and
But
uh,
you see that this is equivalent to just making the area of the area of the rectangle.
yeah. So it's
So that's
so
probably how Galileo figured this out.
no, fine. I don't have a problem with that. So t over two times the final velocity is ct, because the slope is c. The slope is c. So this is just ct.
Yeah.
So the distance is 1/2 ct squared.
Yes.
Now what do we know? Okay, we know acceleration is c, velocity ct. All we know is the empirical evidence we have is the distance after 1 second is 32 feet. So 32 is equal to 1/2 c, which means 64 feet per second is equal c. Sorry, 64 feet per second squared, because c is the acceleration. So it's 64 feet per second squared. So after 1 second, it's at 64 feet per second. So c, oh, c is 64. So 1/2 c, 1/2 ct squared, the equation 1/2 ct, but we know c is 64. So it's 1/2 of 64. Oh, so 64 is g. So it's called g. So g is 64. So g is equal to 64 feet per second squared. Okay. And g is c. Oh, g is c. So it's equal to 1/2 gt squared. Okay, that's the equation. So distance is 1/2 gt squared. So g 64 feet per second squared. Let's ask ChatGPT. Is wait, what is g? What is g? What is g? Nine in feet. What is g in feet? Is it 64? Are you gonna answer? Did you answer?
Did I answer?
I'm talking to ChatGPT. Oh my god. What is g in feet? Are you gonna answer? It says 32 feet per second squared. What's going on? Why is it 32? Why are we getting the wrong number? Okay, after 1 second, at the end of 1 second, how much did an object fall by in feet? 32. It fell. What's going on? It fell by. Oh my God. You've hit the free plan limit for chat for GPT
Oh, it's okay.
minus
It's
4.
okay.
Did you
It's
know
okay.
that?
You can continue.
Approximately. Oh, it's 16 feet. That's the reason. It fell by 16, not by 32. That's the reason I got everything wrong.
Yeah, you duplicated things at some point.
It's not 32. After 1 second, it's 16. Okay, that's the reason. So
Yeah,
this is
okay.
16. So this is 32. Okay, everything. This is 32. What else? That's it. So it's 1/2 GT squared. Oh, everything is fine. So we know exactly how to derive everything from first principles. Okay, that's all I wanted. It's a good day. It's a good day when you finally know how to prove Galilean acceleration and Nicole Oriane acceleration from first principles. Amazing. What an accomplishment. How long have we been here? It's an hour and 20 minutes. Okay, what else do we got? What else do we want to do with our lives?
Could go to bed at this point.
Yeah, my arm hurts so much. I'm growing old. I'm dying. Okay, yeah, I think we should try to go to sleep.
Alright.
I think we've done enough. Tomorrow we'll continue with the paper. Are
Yeah,
you working
okay.
tomorrow? Tomorrow is a work day for you, or is it a free
Yeah,
day?
it's a work day. It's always work day.
Okay, so I'll hit you up, and we'll work during the day when you are working. You'll just listen. It's good enough. I just
Yeah,
need someone to
as
listen.
usual.
Yeah.
Alright.
All
See
right.
you.
Thank you. See you. Bye. Okay. Leave this. Leave that. And thank you, Nicholas. Thank you very much. Thank you, everyone. I hope you enjoyed it. Let me just fix writing the paper. No, we didn't. We ended up not writing the paper. So let me change the topic. So we just did. All we did was uh, derive falling body. So what is it? Falling body acceleration equals c, then v equals ct, and d equals 1/2. Well, it's at squared. It's 1/2. So let's just say it's at acceleration under constant acceleration under constant body under uniform acceleration. So v equals a acceleration a, v equals at. Derive falling body. Falling body. This is Galilean. So Galileo and Nicole Durian, geometric. So no one has done this. This is the first YouTube video to do this. Geometric de. What just happened? Geometric derivation of a falling body under uniform acceleration. Okay. Galileo and Nicole Durian's geometric derivation of a falling body under uniform acceleration. And in the description, we'll say uh, acceleration equals A, V equals AT, and D equals 1/2 AT. Oh my god, my keyboard is so shiny. AT squared. 1/2 AT squared. So we're doing the derivation. Unbelievable. Save. So no one has done this in the history of YouTube. You know what? Let me check. Has anyone ever done this? We can. Which one we should pick? I guess this one is fine. Oh, we didn't finish watching this one. Ultraviolet. We need to finish watching the ultraviolet. So let's just open a new YouTube tab and share. And let's look for Galileo. Geometric derivation of falling body. Let's see if anyone has done this. Oh, I'm doing it. Amazing. So in case somebody searches for this, I would be the first one, I guess. Me watching me. Okay, Galileo's measure of gravity, the law of falling bodies. So they didn't do Galileo's geometric derivation. Galileo's thought experiment, how to prove the law of falling bodies in your head. What do you mean the law of falling bodies? What do you mean law of falling bodies? The actual geometry? No, this is just the principle of equivalence. This is not the law of falling bodies. This is just the equivalence principle. This is the Galilean equivalence principle thought experiment. Falling body demo. Deriving Galileo's free fall equation. Let's see, 13 minutes. So maybe he did it. Yeah, it looks like he's doing it. Is he doing it?
And where we exactly start measuring, we exactly start measuring the moment I drop it. Definitely prove it again by using midpoint formula. I'm going to replace this one wherever I see the red. So x minus x naught.
No, he's not using geometry. What is he using?
At, get the same thing again. Anyway,
no.
So let's move on. X minus x naught is equal to 2 to cancel v naught t plus half a t squared.
What is that?
Okay, so this is the formula I wanted to prove. Now, I'm going to talk about this formula for next few seconds, and I'm going to show you an example.
Where's the geometry?
Are the same thing. Half a t squared, or you can write it as y is equal to y initial plus v initial t. If I drop is the vector, but v. So an apple fall from, let's say an apple fall from one, I don't know, to their weight, but 1900 year later, Galileo said that something different, that the object mass has nothing to do with. Today we are actually going to talk about the free fall. So that Greek philosopher Aristotle said that object in free fall, the speed of the object is proportional to their weight. But
my God, he has 1.2 million subscribers. Wow, that's a big channel. When did he? And he did this just a year ago. 0 comments. 624 views. Not likely. Something is wrong. Something is very wrong. 1.27 million subscribers. 0 comments, 624 views. Not likely. Not likely. Something is wrong here. 6 likes. Very unlikely. Something is wrong here. Something is very wrong here.
year later, Galileo said that something different, that the object mass has nothing to do with the object speed when they fall.
I think he's Filipino by his facial features. I think he's Filipino.
This is what we're going to try to understand by four kinematics equation. Now, today I'm going to give you proof of the most famous one, d is equal to VAT plus half AT squared. But I want you not to remember any equations, is because the memorization is crime. And also, if you do memorize, you would not be able to read the mind of Aristotle or even read the mind of Galileo, because how Galileo was able to correct the mistake made by Aristotle, you would not be able to understand that. So do not memorize them. Understand them. How do you understand them? By deriving them, by prove them, when you can prove them, then you'll be able to use these tools to read the mind of Aristotle and also mind the Galileo. With this, so we'll start with average velocity is x minus x naught over t. I can write t minus t naught, but t naught is equal to 0.
1 second, let me check an email. Yeah. La 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 la. Not interesting. Nope. Nothing critical. We're good. We're good to go.
I can write t minus t naught, but t naught is equal to 0. X minus x naught is equal to v naught t. Now I'm going to make v naught t red, so I will have v naught t over here. V naught t is equal to v naught plus v over 2. I proved that in the class a few days ago, so I'm using this. We can definitely prove it again by using midpoint formula.
So average velocity is final velocity plus initial velocity divided by 2. That's the average velocity. Okay.
I'm going to replace this one wherever I see the red. So x minus x naught is equal to
X minus x naught. Wait, what is going on? He says here average American flag. So he's in the U.S. Okay. So average velocity is distance divided by time. Then from this he gets the distance is the average speed times time.
put this red thing over here, v plus v naught over 2, and then
And the average velocity is v plus v over 2. That's incredible. So he's already getting the 1/2.
then bring down the t.
Right, you have the t, yeah.
So now the second thing I'm going to do, I'm going to make this one blue. So I'm going to write this over here. So v is equal to v naught plus at. I already proved that in the class.
Oh, so you're saying, assuming a constant acceleration, the definition of v at any t, v as a function of time, is some v initial plus at, well, assuming that velocity changes relative, well, velocity, basically what Galileo said. This is not Galileo's derivation. It's a nice derivation. It's not deriving Galileo's free fall, but it's not Galileo's derivation. Very nice derivation. However, this is not Galileo's derivation. Galileo used geometry, and you're not. You're not using, there's no geometry. It's a nice derivation. You are assuming, just as Galileo did, you're assuming constant acceleration. So velocity is v equals ct. So that's all you need. That's good.
So I'm using this as an axiom. So x minus
No, I wouldn't say you're using it as an axiom, but you already derived it from first principles. That's fine.
x naught.
This is basically the triangle. The height of the triangle, and t is the base of the triangle, and the slope is a.
Is equal to, I'm going to replace this right here. So I'm going to write v naught plus at plus v naught
So v naught plus at is v. And you're adding another
over
v
2
naught over 2.
times t. So now I'm going to write x minus x naught is equal to, now do you see that I have a blue v naught and I have a red v naught. Blue v naught, red v naught, I have a 2 v naught. So 2 v naught plus at over 2.
Very
and
good.
everything multiply by t.
Good.
So I have x minus x naught. Now I'm going to use some properties of algebra. So 2 v naught over 2, I'm going to make this t red so you know how I can move it around. So I'm going to put the plus sign. You see the plus sign over here. I'm putting the plus sign over here. Now I'm going to write
1
at
half
over
at
2.
squared. That's amazing.
And then I put t over here. All right, so the distributive property allow me to do that. If you distribute that, you're gonna go back, get the same thing again. Anyway,
Good.
so let's move on. X minus x naught is equal to 2 to cancel v naught t plus half a t squared.
Amazing.
Okay, so this is the formula I wanted to prove. Now, I'm gonna talk about this formula for next few seconds, and I'm gonna show you an example. So x minus x naught is equal to v naught t plus half a t squared. So you can write it as x is equal to x naught plus a v naught t
Very good.
plus half.
So he's moving x naught to the right side.
You can rewrite this equation as y is equal to y naught plus v naught t plus
He's switching
half
to y.
a t squared. Or you can write it as y is equal to y initial plus v initial t plus half a t squared.
Wow.
Or you can write it as
Why
d
is he-
is equal to d initial plus v initial t plus half a t squared. They all are the same thing. Different ways of writing. However, let me now give you an example. Let's do a case study. Let's say I drop this from this height. I drop this pen from this height. If I do that, you saw it falling. Now we can calculate the distance.
Okay, now he's going
can
to
also
use.
calculate the displacement. If I drop this, dropping means
So now he's going to derive. He's going to use this equation.
let it go. In the moment here. So if I say x, that means I'm going to let this one 0. So d is equal to vit plus half distance. Then this formula is this formula. V goes to 0. When you drop something, initial velocity is 0.
0.
Gt squared. Okay, so now you write z, and you put a vector. You can write t squared. This vector means
Good.
is always, this is not, and the gravity is, or
Okay, very nice.
let's say
Very nice, but irrelevant. That's not what I'm looking
today
for.
we are actually
So this is Galileo's law of
Hi,
falling
everyone.
bodies.
Welcome back to Dave's Math Channel. I'm your host, David Tear, and today I'm going to. Hi, everyone. Welcome back to Dave's Math Channel, and the graph of that is a parabola. I'll get more. You go up or go down.
No, if you say
So you're supposed to
parabola,
imagine
you don't.
this example.
If you're using a parabola, it's not Galileo's derivation. So he's not doing Galileo's derivation. Where's the derivation?
I have almost the same speed if you do this. I just don't think that Galileo did this. But regardless, he did discover the law of falling bodies. So what does the law say? Well, it's a mathematical law, and pretty much all of science, especially physics, is really math is the key to understanding physics. So these are mathematical laws, and I guess I have to explain them to you, but they're not that hard. I mean, so here's what you're supposed to imagine. Imagine you're throwing an object like the ball. Initial speed to discover to accelerate gravitational force. It's enough to know the second square equation of falling, because then there's any rating it speed, distance.
Okay.
I imagine
He's not deriving the equation.
One.
He's
You're
just
supposed to
talking
imagine
about it.
initial speed of the ground. It's going to form.
Okay, he's just talking about how to use this equation.
So again, you would parabola. You mentioned parabolas earlier, but
Projectile
becomes
motion
a little more
equation.
complicated when you include a thing. I mean, it is interesting.
It's interesting
Pretty
that
much tell you everything you know. You can consider the case where it's not going to move in an arc trajectory motion, but not that much more before not going straight up or down.
this is good for projectile. This is good for military. Military could have found it very
you get
good.
a nice parabola, which is what this graph is showing here. And if you want to get a formula, it's a vector, and you can think of the x eventually gets to 0. And
Yeah, that's pretty amazing. You can do.
3D.
This is projectile. This is trajectile
another picture
analysis.
Projectile motion. But we've known the Earth. Think of launching the Eiffel Tower in a straight horizontal direction. Well, depending on the speed, the initial speed v0 that you launch at, that you shoot the cannons off.
That's good. So
it's going to go a certain.
So Galileo could have already figured this out because he could have calculated the parabola, and basically what you need to do is the parabola needs to be right. It's a parabola, a bigger parabola, a bigger parabola. You need. So the question is, what should your velocity be? What should your horizontal velocity be so that this is the parabola ends up what? Well, I need to think about this.
Distance before it hits the ground, and you could actually use Galileo.
Oh, you want to be able to calculate the distance equals the entire planet. It needs to land back at where you launched it from. And in that case, it should enter an orbit, maybe. Right. So if you assume the height, a certain height and a certain velocity, that's the trajectory where you launch it from, and you're saying, okay, it needs to land here. No, it needs to land back here. How do you do that?
Galileo's law of falling bodies to approximately how far it goes, for small speeds. But then as the speed gets larger and larger, since the Earth is round, it actually goes farther than you expect because the Earth is curving away from where the cannon would have landed otherwise. And if you launch it fast enough, Eventually, it'll go into orbit. I mean, it looks like they show 5 projectile motions here. The fourth one, it just barely grazes the surface of the Earth. It looks like it lands, in near Asia somewhere. But if it did a little faster, it'll actually go into orbit, and in the absence of any air resistance, if it's in space, it'll just keep going.
Okay, but that's not Galileo's derivation. It is an interesting problem to look at.
Reference per second. Galileo's law, falling bodies, and then you do it a little faster, you get to B, and now you can kind of.
So Galileo already figured this out.
Kilometers per second Earth day.
That's interesting. So Galileo already knew this. That's amazing. But that's not Galileo's derivation. Who is this? From Kepler to Einstein, integration. Okay.
Hey, Shalom Duvid here. Welcome back to our metaphysics series.
Metaphysics?
So,
what is that? Let's see.
Aristotle several thousand years by other here. We're also going to be, as you've seen, the two balls come down, and Galileo was talking them frame by frame so that we can follow motion to balls at a measurably slower speed than the heavier lacrosse hits the ground, about 100 milliseconds later. Let's review. The profile area of the falling object, A, and our. Here the second concept, the terminal velocity will dominate. And the object, why the wiffle ball falls slower than the lacrosse ball, and why the practice golf ball falls slower than the regulation golf ball.
What is he talking about?
Every object falling through a viscous fluid like large and heavy, neither of the water it reached terminal velocity.
I don't know what he's talking about. I don't see any geometric derivation. Proving Galileo's theorem.
In earlier videos, we learned that Galileo had correctly predicted the motion of freely falling bodies.
Oh, there it is.
Down an inclined plane.
Oh,
AC,
very nice. There it is.
AC.
There it is.
Time. And based on it, Galileo postulated his time-squared law. According to the time-squared law, for uniformly accelerated motion, the total distance covered by a body is proportional to the square of the elapsed squared law, and the law of fall resulted in what we know body to slide along any chord of a circle is the same as the time taken to fall vertically downwards across the diameter of the circle. To prove Galileo's theorem, let us consider that a ball is dropped freely through a distance equal to d. Now let us construct a circle with diameter equal to d. Let us then suppose that the ball slides down an inclined plane, AC, where A is the top of the inclined plane.
I wasn't thinking that's how he proved it. I had a different proof.
As you can see on the screen.
Is this
AC
how he proved it?
Distance equal to prove all vertically downwards across the diameter of the circle.
The time it takes a body to slide along any chord of a circle is the same as the time taken to fall vertically downwards across the diameter of the circle.
To prove Galileo's theorem, let us consider that a ball is dropped freely through a distance equal to prove vertically downwards.
The time it takes a body, this is his theorem, to a body to slide along any chord of a circle. So there is a chord of a circle. Okay, so there is a chord, okay. The time it takes to slide that chord is the same as the time it takes to fall the diameter. Slide along any chord of a circle is the same as the time taken to fall vertically downwards across the diameter of the circle. So every chord is equal to the diameter? All the chords are equal? All the chords take the same time? What? All the chords take the same time? Wow. Wow. All the chords take the same time. I would never ever imagine that. Okay, so every chord creates a right angle, a right triangle. So this chord creates a right triangle, but there's another right. There's two right triangles, but they should have this angle and this angle are the same. Oh.
Let us consider that a ball is dropped freely through a distance equal to d. Now let us construct a circle with diameter equal to d.
That has nothing to do with the derivation of 1/2 at squared, 1/2 gt squared. Or does it? Time taken. So t is square root of 2d over g, meaning gt, I don't know, whatever. Oh. So where's, so it's just from geometry that he's doing all this. Just from applying Galileo's theorem, we can easily prove that the period of a swing of a pendulum is independent of the amplitude of swing. Wow. Unbelievable. But this is a good proof. I'm too tired at this point. Good.
Hey.
So what I proved is incorrect?
The world
can use
Good
any
idea.
complicated.
Galileo's falling bodies.
Said something about it. Who? Okay, so today we're gonna of Pisa and might have time.
No,
And that's what they
it's nothing. It's really okay. What's about this guy?
And the experiments were conducted, causes a downward acceleration. Gravity. Of law of motion states S, which is the
What do you mean? How do you derive it?
when an object was dropped, 1 kg mass object.
I don't know. What else?
Hi, welcome to my math tutorial. Hi, welcome to my math tutorial. In today's video, we're gonna talk about application of differential equation. We know
Oh,
we have
application
I
of derivation. Okay, no
and
derivation,
G.
just application. I don't care. The law of falling bodies. Law of falling
Hi
bodies.
guys, my name's Nicole Goodman, and what a moving object so he can measure its speed. I also learned that the
Physics experiment. Free fall.
This is lesson direction downward. So if we have a long tube that we're able to remove.
Whatever. Okay, I'm done. It's good stuff. Oh, free fall problem. No.
Let's go over Galileo achievements. Important mathematically, it can be that the distance duration due to all these formulas.
Lives New Jersey. Done for the experiment.
Okay, I'm done. It's good enough. All right. All right, everyone. Thank you. See you tomorrow. Bye.